Hello everyone, this is Mr. Couple. This is PHYZR number 16, Investigating Wavelength. This is from the Waves chapter, it's page number 5. Today's lesson will be deriving the Wavespeed Formula, which is an equation which relates the speed of a wave to its wavelength and its frequency. We'll be doing this through a thought experiment using a pencil and a paper. Let's get started. Suppose a pencil moves up and down at a steady rate. What happens if the paper is pulled to the right? So the pencil is in contact with the paper and it's steadily moving up and down. What do you think will happen if we pull the paper to the right? Let's go ahead and give that paper a pull. As you can see, it makes a sine curve, or a wave shape. The question here is, what physical action determined the frequency of this wave that we just created? What was the physical action that determined the frequency of this wave? There were two actions that we took. One was moving the pencil up and down. The other was moving the paper. And since the frequency is the number of cycles per second, then the event that was repeating, the action that had a frequency, was moving the pencil. So the quicker we move the pencil, the higher the frequency. The slower we move the pencil, the lower the frequency. In other words, the frequency of this wave that we've created was determined by the source, the oscillations of the source. Well, what physical action determined the speed of this wave? And that would be the other action we took, pulling the paper. In other words, the medium, the material that carries the wave. And this is actually true for all waves. The frequency of any wave is determined by the oscillations of the source. And the wave speed is determined by properties of the medium that the wave travels through. So we'll be using this analogy of a pencil and a paper to try to understand the relationship between the speed of a wave, the frequency of a wave, and the wavelength of the wave. Before we do that, let's label the points on this wave. First of all, we notice from the shape, the up and down motion of this wave, that it is a transverse wave. We can see the crest here and the trough here. In addition, we see our wave has an amplitude as well as the wavelength. So now let's do some investigations into the wavelength and how it depends on the frequency and the wave speed. First, what happens to the wavelength if we increase the wave speed? So that means we need to pull the paper faster. So what will happen to the wavelength if we increase the wave speed? I want you to think about this and try to predict what will happen. What we're going to do is pull the paper on the top normally, as we did it the first time. But the paper on the bottom, we're going to pull it at double the speed. So we're going to pull the paper twice as quickly as the one on the top. And let's see what happens to the wavelength. Here we go. So the wave at the top was going at half the speed of the wave on the bottom. And you can clearly see a difference in wavelength. So we conclude that increasing the wave speed, as you can see, increases the wavelength. This is a direct relationship, so symbolically we can write this as lambda directly proportional to wave speed. V is for wave speed. So now let's see what happens if we change the frequency. So rather than changing the wave speed, let's try changing the frequency. And this time what we'll do is we'll pull the bottom paper at the same speed as the top paper, but the pencil will be oscillating twice as fast. So we will double the frequency of the pencil on the bottom. What do you think will happen to the wavelength if we increase the frequency. Let's give it a go. Again, we notice a distinct difference in the wavelength between these two waves. So the wavelength does indeed depend on the frequency of the source. In this case, we notice that increasing the frequency, which is the wave on the bottom, caused the wavelength to decrease. This is an inverse relationship. Mathematically, we can express this as lambda proportional to 1 over f. We notice that dividing by a larger f, increasing the frequency, will decrease the wavelength. If we put our findings together, we have that increasing the wave speed increases the wavelength, the direct proportionality. We also found that increasing the frequency decreased the wavelength, an inverse proportionality. Let's combine these two proportionalities together, and we see that lambda is proportional to velocity divided by frequency. Well, now that we have all the quantities present, we don't have to keep that proportionality sign. Instead, we can write an equal sign. Now I'll just do a little bit of algebra to manipulate this into a more nicely written form in which we solve for the wave speed. So we'll multiply both sides by frequency. That'll cause the frequency to move to the left side. And now we'll just rearrange the variables, and we have the Wavespeed formula, which says that wave speed is equal to wavelength times frequency. All we need now are to remember the units of each of these quantities. The units of wave speed are meters per second. The unit of wave length is meter. And the unit of frequency is hertz. So this is a quick way of deriving the Wavespeed formula by a thought experiment. Hope you guys enjoyed this lesson, and I'll see you in class.